Hello, everyday statistics, and welcome to lesson 2.5. Today, we're going to be talking about a regression line. You also might have heard this referred to as a line of best fit or a least squares regression line. We'll be looking at the least squares regression line today. All right, so today we're going to just be given a least squares regression line. We're going to make a prediction using the regression line, the equation. And then we're going to calculate a residual, and we're going to also talk about how to interpret the slope and y-intercept of a regression line. So if we look at these things, they're always going to be in this form. Y hat, very important, right? Y hat says that we're going to be making a prediction. That's going to be equal to a plus bx, where a is our y-intercept and b is the slope of the line. So these are just linear equations that we're going to be looking at. So an interesting thing about regression lines is they're used to make predictions about some explanatory and response variables. Only problem is you're not allowed to make a prediction outside of our observed value. So in this case, our lowest observed value is over here, and our highest one, so I don't know, maybe that's 10,000 miles or something like that. And then our highest observed value is over here at, I don't know, I would estimate that as maybe maybe it's 150,000 miles if I was going to estimate it. I'm not sure if that's what it is. Problem is we're being asked to make an estimate for something that's at 300,000 miles. And that's way, way over there, right? So it's outside of our observed values. And if we're trying to make a prediction for something outside of those observed values, what we're doing is we're extrapolating. So this prediction would be an extrapolation. Now, if we wanted to go ahead and estimate, maybe we didn't know what was going on, here, maybe at, let's say, 90,000 miles. Now, if we wanted to make an estimate for 90,000 miles, we would be just fine. We would not be extrapolating because it is within the range of our highest and our lowest observed value. That's those dots there. So definition of extrapolation is there. We kind of talked about that. All right. So another element that we'll get from our regression line, the equation, is we'll be able to calculate a residual, right? It's the difference between the actual value, right, our observed value, and the value that we would predict using our least squares regression line. So if you're wanting to calculate a residual, and we're going to do that later on here in the lesson, we're going to use this equation. So here's a nice picture of what a residual is, right? So if we have, this is our observed value, or a given value. And then the value that's here on the regression line, this dot here, is our predicted value. And what we're looking at is our y values. Okay, so we're looking at y values. So the residual is just going to be this distance here, right? So we're going to subtract our observed or actual minus our predicted value. That's going to give us this residual. Our residuals can be negative, right? If we have our observed value is below the least squares regression line, our residual will be negative. If we were, say, calculating this particular residual, right, the difference between this observed value and this predicted value, you would have a positive number for our residual. And we'll work through this as we go 3. All right, I told you that in the regression line, y hat equals a plus bx. A is our y-intercept and b is our slope. Right? So if we're going to be interpreting the slope and the y-intercept is our predicted value when x, or our explanatory variable, is 0. And the slope tells us how much we would predict the change in y to be for each unit increase in x. Um, super, super important to include the word predicted, um, because we are not making any sort of actual claim about the real value, right? This is a prediction. I'm not sure. All right, so let's go ahead and get down to it. Let's do an example. So we're wondering if cut flowers benefit from having sugar in the water. So we want to know if we add sugar, does it help them stay fresh? So they went and got 12 carnations selected randomly. When they got home, these students prepared 12 identical vases, exactly the same amount of water. They put 1 tablespoon, right? So they've got, what are their treatments they're putting in? They have 1 tablespoon of sugar, 2 tablespoons of sugar, or 3 tablespoons of sugar. And then we have 3 vases that have no sugar in them. So let's see how many hours each flower continues to look fresh. Looks like they got a regression line with y hat equal to, or the equation of a regression line with y hat equal to 180.8 plus 15.8x. We can see the values of the 3 vases, right? So you can see that these guys had no sugar. These are the 3 vases with 1 gram of sugar, 3 vases with 2 teaspoons, of sugar, and the one with the 3 teaspoons of sugar. So it appears that adding more sugar is actually causing the flowers to stay fresher longer. So let's go ahead and get to 1. I guess they're all number 1. That is interesting. We'll have to fix that possibly. So let's go ahead and calculate and interpret. No, sorry. Yeah, let's do a residual first. Calculate and interpret the residual for a flower that had 2 tablespoons of sugar and was fresh for 204 hours. Let's go ahead and look at this on another page. Excellent. So we want to calculate and interpret this residual, and we're going to need our least squares regression equation. So that is y hat equals 180.8 plus 15.8x. Okay, so keeping in mind that what we're going to do is we're going to have our observed, or our actual, minus our predicted value. Remember, these guys are all, we're looking at y values, right? Or the values of our our response variable. So it looks like we had an observed value of 204. What would our predicted value be? So in order to find our predicted value, we're going to take our our predicted value is y hat. That's what y hat is. And we want to know, what would our predicted value be for 2 tablespoons of sugar? So what we need to do to predict that is to just input 2, or substitute 2 for x, and we're going to calculate this value. Another way of saying that is that this is actually our y minus y hat. Okay, so we're given this y value, and now we're going to go ahead and calculate our y value. And after I put that on my calculator, I got that we had 212.4. And remember, that is in hours. We'll go 212.4. So that would be negative 8.4. So that is our residual. So how do we interpret that now? Because we've done the calculate part. Now let's get the interpret part off. So our predicted value, or the predicted value, right, it's less than our actual value. Or actually greater than, sorry, the predicted value is greater than the observed value. So let's put that into context as well. What does that mean? What that means is that we actually predict a flower to last longer with 2 teaspoons than we actually observed. So in other words, we could say that our predicted value will be off by 8.4 hours. Excellent. All right, so the next thing that we need to talk about is going to be interpreting the slope and y-intercept of this regression line. So let's get this out on a new page and have a look at it. So first of all, let's identify that our y-intercept in this case is 180.8, and our slope is 15.8. So what does the y-intercept tell us? The y-intercept tells us that when we use, or we could say when no sugar is used, right? That's when x equals 0, or I could spell when no sugar is used, right? We want to put these into the context of the question. Of course, that means that x equals 0, right? That's the value when x equals 0. But that doesn't give us context for the question, right? So when x equals 0, what does that mean? That means that there's no sugar added to the vase. So when no sugar is used, we expect the flowers to appear fresh. For how long? It looks like for 180.8, and our units are hours. So there we go. That one is in context. Let's talk about what the slope means here. So 15.8. The way that we are going to interpret this is that we're going to say for each unit increase in tablespoons of sugar, or was it teaspoons? Let's look at our units. We're looking at tablespoons. All right. For each unit increase in tablespoons of sugar, we expect, and now we're going to talk about our response variable, which is hours of freshness. So we're going to expect the hours of freshness to increase. And now we're going to input that value of our slope by 15.8 hours. Perfect. And you can literally use this exact same format every time. For each unit increase in, insert your explanatory variable right there, right? Which is tablespoons of sugar. We expect and then you can just input your response variable here. You will get that right every time, right? So for each unit increase in, insert explanatory variable, we expect the insert response variable to increase by whatever this slope is. Okay, we interpreted the slope and the y-intercept. Now the question is, would you be willing to use the regression line to predict the hours of freshness for a flour that received 10 tablespoons of sugar? Well, here we are at 3 tablespoons, right? So our observed values, or our actual values, only range between 0 and 3. That means that I could only make predictions for amounts of sugar that are between 0 and 3. So for instance, if I wanted to estimate how fresh a flour would last if I put 1.5 tablespoons of sugar, that would be fair. But 10 is just way, way out here, right? So it's outside of our actual or our observed values. So we would say no. The value 10 is outside of our observed values or our actual values. I like to use the word observed. Values. This is extrapolation. Awesome. And that concludes our example for lesson 2.5. So today we did these things. It was awesome. Thank you guys so much for watching. I hope that you're having a fantastic day. And if you're not, I really hope it gets better. Thanks again and take care of yourself.